Hey guys, it's Mr. Sheeline here. This is going to be the video covering Unit 5.2 notes, conservation of momentum, and collisions in one dimension. So hopefully you can, or at least what should be implied here is that we are going to be getting into collisions in two dimensions in the next set of notes. I just want to focus in and practice one dimension before we move on to that, because two dimensions does get a little tricky, especially when we have to deal with hitting things not so perfectly. More or less getting into some real life stuff here to a certain extent. So let's go ahead and let's just go to it. So how can we look at conservation of momentum? How can we look at that phrase, that technically that law, and what can we take out of it? So for the most part, what we can boil it down to is this little summary. We'll get into the actual full description of it, but this little summary, pretty much the total momentum in any closed system will remain constant. So, and this is tied to a video here with Richard Garriott. I would like you guys to watch this. We're not going to watch this in this video, but I'll post this along in the I'll post this in the Google Classroom post for you to watch. So please watch it. He shows you, conservation of momentum in space on the ISS. It's really, really cool. He uses these tennis balls, as you can see. We're going to skip right past that. Okay. So this is pretty much what we're going to be looking at, or at least this is one kind of collision that we're going to be looking at here as we talk about the conservation of momentum. So what I want you to notice here is that you've got two significantly and different, or I should say, you have two cars here that have or automobiles that have significant difference in both mass and velocity and also momentum. As you can see here, we have the truck over here. Before he hits the truck has negative 60 kilograms by meters per second. So you could say that it has 60,000 units of momentum, while the car here, before it hits the truck, has 20,000. Now, what we can see here, though, is that after the collision, we can see here, this is a great example of where momentum has been conserved, where you now have the truck transfers all of the energy, and thus the momentum changes from the truck and is then exerted onto the car. We see here it's negative 60, which just means that it's in the opposite direction as the car. And we can see that the car being a positive 20, that just means that it's in the positive direction. And then once they collide, we see the car takes in that energy, is now moving in the opposite direction from once it started, and also that its momentum is equal to the difference between the two. So how do I know that? Well, simply, it's just 60,000 from the truck. Really, I should say it's 20,000 from the car is what I really should be organizing this as, minus 60 from the truck, which is going to give you negative 40,000, okay? That's one way you could write it. You can write it and you can set up the operation differently. That's just how I did it. You could say it's 20,000 plus the 60,000, but it'd be the negative 60,000. Same difference. But what the point here, the point of this little demo here is showing you that this is what we are talking about when we're talking about conservation of momentum during collisions, and what we're going to be practicing here. Okay. But before we can get into those collisions, the types of collisions, we have to know really we have to have a good understanding of what the law of conservation of momentum is. So here's that full written out portion of it. So when two or more objects collide, the collision does not change the total momentum of the two objects. Whatever momentum is lost by one object in the collision is gained by the other. Okay, the total momentum in a closed system is conserved. And here we've got sigma. We're using sigmas to denote the sum of these of the momentums. And this is really what we're looking at. We're looking at the initial momentum before collision. Okay, we've got the initial momentum before the collision, and we're going to be looking at the final momentum after the collision. Okay. I think the next slide is pretty much just another way of describing this. Or is it the video? So I would try to play this video. I've tried this before in another attempt making this, and it just doesn't work out. So I will also post that on this post, on this Google Classroom post as well. I need you to go watch it. And what I want you to do is I want you to make predictions. Each time there's a new set of balls that are pulled back in that Newton's cradle, predict what's going to happen, okay, when you're thinking about the conservation of momentum. So here is, we're getting into the mathematical parts of this. So in a system, okay, so in a system here of momentum, it's clearly going to be the momentum of one object plus the momentum of another object. Now, obviously, we're working with vector quantities here, so direction does matter. Direction makes a big impact and tells us how we're supposed to, or at least should let us know that, hey, we've got two objects moving in different directions here. You've got to assign one as being positive, one as being negative. Which one is it going to be? So keep that in mind. But really, it's just to say that in a system here, we've got momentum of one object, momentum in the other. So here's the law of conservation of momentum again. The total momentum of the system before the collision always equals the total momentum of the system after the collision. So let's just say that again. What we've already seen in the previous slide, that the initial momentum of the system should equal the momentum after the collision, okay, the final momentum. And then you can just break it down like this. So you've, again, momentum of the first object, momentum of the second object, and then over here, momentum of the first object, momentum of the second object, this being before, and then this being after, okay? Now, it doesn't always have to be two objects. We're really just going to be focusing on two objects, because when you introduce three, it does get pretty tricky. It gets pretty tricky in having to separate different systems, and then having to know what times that they need to be incorporated, distances that objects travel before they collide with another object. It gets pretty complicated and pretty quick, and that's something that we really won't go into. That's more of college level physics that we're going to kind of stay away from, because I want you to just know the fundamentals here. I want you to just understand what momentum is and how we then attribute and also or calculate it in collisions. Okay, so I've already mentioned this. It's something we can never forget, and this is why I'm emphasizing direction so heavily in this unit. Momentum is a vector quantity, so direction is super important, okay? So here's a check your understanding. Like usual, this will be in a separate video, so keep an eye out for that, or I'll just post it in this post. But anyway, okay, collisions. So what is, or before we really get into understanding the different types, we should really know and have a solid basis and idea of what a collision is. Probably already know what a collision is. We probably have either been in one or seen one. When it comes to like automobiles, we see them all the time. They're happening all the time. Even you reaching down to grab a pencil, that's a collision, okay? And so like it says here, so when two moving objects make contact with one another, they undergo a collision, okay? Conservation of momentum and Newton's third law of motion are used to analyze all of these collisions. So remember, Newton's third law is this, that every action has an equal and opposite reaction. Okay, something to always keep in mind that in order to walk forward, when you push your foot off the ground has to push back on you in order to move forward. If like in the what you'll see in the first check your understanding, I believe it's the first check. Yeah. And the first check your understanding there, keep that really, really locked in your mind that the ground is, the boat that dude is standing in and eventually start walking on. It's not on, it's not locked in. So he'll go one way, and we should expect the boat to move, maybe not so much the same direction. Okay. So during collisions, external forces are ignored. Pretty much what that means is that external force, and that word external forces, we really won't get into internal versus external forces. We typically do in momentum, but we're just going to kind of push that aside. All you need to know is that external forces are like friction. They're like normal forces. They are gravitation, or well, gravity is internal. Sorry, they're forces that we just ignore because they are forces that overcomplicate things when we're just trying to practice the fundamentals. Definitely something that an engineer would have to always watch out for, because of course, friction is a force. Friction takes up energy, and you need to know how much energy is going to be taken up, how much material is going to be used up due to that friction in whatever system or machinery you're making, or whatever project you're trying to put together. But for us, we're going to ignore external forces, and then that's that. Time frame of the collisions is very short, as we know, and not only is the time frame short, but the forces are high in magnitude. Yeah, this word right here, that should be high in magnitude, not forces. Magnitude. Oh my goodness. I think some would say that I need a new set of stylus. Magnitude. Low body. Okay. So the forces are high in magnitude and short in duration, relatively speaking. Okay. And then I've got this little picture, this little diagram down here. So the collision between two billiard balls on a friction-free surface occurs in an isolated system. The only unbalanced forces occur from within the system. So that's to say here, more or less, that the things that we're really looking at are the applied forces. We're not really looking at the normal force here. In this case, we're not looking at the gravitational force that is affecting the billiard balls, because of course that would mean then we would have to factor in friction to some extent, or at least at some microscopic level we would have to. Now, when I said that gravity is an internal, that's more of gravity, just the force of gravity, generally speaking, not so much the force of gravity applied to an object. Okay. So again, we don't really have to worry about that, just to clarify. Okay. Now, here are the three collisions that we're going to be looking at. And this may look like to be in a weird kind of order. You'd think that we'd start with elastic, move to inelastic, and then finish with completely inelastic. It's in this order because this is the order that we're going to be looking at these. And realistically speaking, the two that we're really going to be working with when we're working with one-dimensional collisions and one-dimensional momentum, they're going to be completely inelastic and elastic. And I'll get to that in just a second. But we have all three of these here. We have inelastic, completely inelastic, or another way that some professors and some other teachers refer to this as perfectly inelastic, and then elastic. And then real quick here is how we know the differences between each. So in inelastic collisions, deformation of your objects occurs, kinetic energy is lost. In completely inelastic, objects stick together and become one object. Deformation does occur, kinetic energy is lost. So the biggest difference, obviously, between 1 and 2 is the first one in completely inelastic. Objects stick together and become one object. So that's a main, huge, key difference. And then finally, elastic, no deformation occurs, and no kinetic energy is lost. So hopefully you can see maybe why it is that we're going to be focusing on these two. Now, most, and as we'll see in the next slide here, most collisions are inelastic in the real world. There's deformation of your objects, kinetic energy is lost, and a lot of times objects bounce off of one another. They don't become one solid object. Okay. Now there are obviously quite a few that do merge. Say in an automobile wreck, there are times when two cars collide and they more or less stick together, or at least they become one object. But for the most part, most of them are inelastic. But the reason why we don't look at them, we'll get to here in just a minute. So collisions, part of it, remember, and since we're referencing it, remember kinetic energy is a huge part of it. Remember, kinetic energy is the energy of motion. And as we saw in inelastic collisions, both perfectly or completely inelastic, and also in inelastic collisions, kinetic energy is lost. Kinetic energy is lost in the form of heat, in the form of friction, in the form of a number of other things, in the form of sound. It's transferred as to other kinds of energy. Whereas in elastic option or collisions, there is no loss in kinetic energy, and we'll get to where you would see that. But anyway, I thought it'd be a good idea to bring back this equation just in case, because there will be some problems down the road and some activities that we're going to do where you have to calculate the kinetic energy of an object, and then with that you can then find out the momentum, and then x, y, and z. So okay, and then again, in collision calculations, momentum is conserved. So remember, that's why we went over conservation of momentum. When you have two objects colliding with one another, you should have the same momentum both before the collision and after the collision. So hint, hint, that's going to be a great way to double check your work. Okay. In completely inelastic collisions, however, calculations of the masses when they stick together, you'll just have to remember that your final momentum is going to be the addition of your two masses, okay, or the masses of both your objects, because they're now one. So, and that's denoted like it is down here. Just keep to remember that in your final, momentum, the mass is now the mass of both objects times the velocity, the final velocity that you calculate. Okay. Okay, now finally get to this. Now, inelastic collision. So the total energy, as we've talked about, total kinetic energy of the system after the collision is not equal to the total kinetic energy of the system before the collision. So energy is lost to heat and sound during the collision. And like I've mentioned, most real life collisions are inelastic. Now here is why we don't really do a whole lot of problems with inelastic. It's because of how close to real life they are. They're decently complicated. And like we've already talked about, the energy, the reason why the kinetic energy is different is because it's lost through heat and sound. Okay. Well, we've already mentioned that when we're working with conservation of momentum, we're going to ignore what's the word here? External forces. Heat and sound, in this case, are going to be external forces. Okay, more or less. Heat will be transferred. That's energy transferred through friction. Sound is going to be more or less friction. It's you have the rubbing of in the collision of atoms bouncing off one another, vibrating wave patterns till they get to your eardrum. Okay, that's all energy, and so we're going to ignore that. And so because we ignore that, we are going to be pretty much just be working with completely inelastic and elastic collisions. Okay, but it's still important to know that these exist, and that for the most part, they're the ones that we see in real life all the time. Now, completely inelastic collisions. So again, we've mentioned this, that when two objects stick together during a collision, that's where you would see completely or perfectly inelastic collisions. So because the objects stick together, they have the same final velocity, and they will have they will both have whatchamadoozits. They will also both have my goodness, they'll share the masses. It'll be the sum of the masses now that they're tied together. And as we can see here, though, the initial kinetic energy is going to be less than the final kinetic energy. And that makes sense because, first you had two different objects and now you have one solid object together. So you should expect to see a change in the kinetic energy at the end during the final, when you measure the final. So that's typical. Whereas the momentum initially is going to equal the momentum finally. Okay. And then, I don't know why that went away. We have our check your understanding. So again, I'll be going over those in a separate video. And then total kinetic energy of the system before the collision is going to be equal to the total kinetic energy of the system after the collision when we are looking at elastic collisions. Now, where do we see these magical elastic collisions? It's like, oh my goodness, you're telling me that energy is exactly the same initially and finally, and also momentum is the same before the collision and after collision. Where do we see that happening? For the most part, yes, you do see this, on Earth. Uh, Very rarely, almost non-existently. This is going to be one of those problems where the only place where you can see this happening is in a vacuum or in space. For the most part, it's very, very difficult to almost near impossible to have a system where you conserve energy completely and perfectly. Even in space, I mean, obviously, there's still a little bit that's going to be lost in the form of heat due to friction. There is going to be a little bit lost due to sound because of friction again. But for the most part, elastic collisions, energy is completely conserved. And then on top of that as well, the initial momentum is going to be equal to the final momentum. So that's where we would see these. Now, that doesn't stop us from trying these out. That doesn't stop us from calculating these on paper because it's an important concept to understand because it does happen. It does happen, and we can observe it. It's just we got to fudge it a little bit, okay? But it gives you a better understanding overall of elastic collisions. Now, when we do these problems, here in the beginning, where I'm going to tell you that they're elastic, I'm going to tell you they're completely inelastic in the problems, as you'll see after, later on, and especially in the check your understandings. And eventually, we'll get to the point where I'm going to ask you to identify them, okay, and we'll practice that. Now, what's really cool about elastic collisions is that we can pretty much break this down into these pretty simple calculations. Because most of the time for these problems, I'm going to say, okay, here's object one, here's object two. They're moving at different rates. They're going to collide in one way or another. It's completely elastic. This is so meaning that initial momentum is going to equal the final momentum. Meaning the energy in the system in the beginning is going to equal the energy in the system afterwards. But the thing I don't have is I don't have the velocity of both objects afterwards. You've got to find me the velocity of both objects only being given the masses, only being given the velocities initially. And maybe their directions. Well, I should say, and also their directions. That's not going to be something you guess. So we can pretty much cheat a little bit here, and I'm going to give you guys the formulas that you can use in order to find the final velocities for both the first and the second, objects within a given system, within a given scenario. And they look like this. So I can go through with you guys the derivation to get these two formula. It will take some time, and it is quite a bit. But if you truly do want to know where these come from, I am more than welcome to, or you're more than welcome to ask, and I'll go through that with you, just so you have a good understanding. What I'll just say that here is pretty much this is a combination of two equations. This is a combination of the kinetic energy equations and also the momentum equations here, which allow us to find, again, the final velocity of object one, we'll say, and then the final velocity of object two. Okay. So again, if you're curious, let me know and I'll go through that with you. If not, that's fine. And just use these. Okay. And they look pretty busy, but when you really look at it, it's pretty simple. It's just you're using mass like it's no one's business. And this can be used for objects at rest. This can be used for if you've got a scenario where one object is moving, one is at rest. If you have a scenario where one or both objects are moving either towards one another or if they are moving in the same direction. So, okay. All right. I believe that should be it. Yeah, the rest will be check your understandings. So that is the notes for Unit 5.2. the conservation of momentum and also collisions in one dimension. Just keep in mind, again, after we get through and have a pretty good solid footing on one-dimensional, collisions, we're going to get into two-dimensional. We're going to be adding a direction or two here, okay, which is going to complicate things a little bit, especially when, that you're not tossing something at a perfect angle. So anyway, so that's the notes. Keep an eye out or look for the Check Your Understandings video. I'll walk you through on how to do that, all that good stuff. And that is the notes. So make sure you guys get a hold of me if you have any questions. If not, I'll see you in the next one.